Hello everyone, I am Prasanna presenting our presentation for the course on Algorithms and Artificial Intelligence. We are here to present on optimal parameters search for distributor recommendation algorithms. The flow of presentation starts with an introduction followed by the dataset, collaborative and content-based filtering, recommender algorithms, hyperparameters tuning, execution of recommender system in distributor fashion, the results, and finally summary and conclusion. First and foremost, let me introduce the three main elements of our presentation today: the temporal graphs, recommendation systems, and hyperparameter tuning. Starting with temporal graphs, these are dynamic graphs whose edge connectivity, or strength in short, changes dynamically over time. Their structure as a whole changes dynamically over time, making them computationally hard to handle. These are mainly used in recommendation systems to capture the interest of users for specific times, thus providing an edge over normal graph structures. They offer more accurate values by incorporating a temporal effect. Now, towards recommender systems. These are derivatives of the machine learning discipline itself and are used to recommend users relevant items. They are employed by online retail stores and similar online product selling businesses such as Netflix to increase the likelihood of product purchases. To achieve more accurate recommendation, the use of temporal graphs is observed in these sectors as well, which in turn is again computationally demanding. Now, coming to the objective of today's presentation, which is to find optimal parameters for these recommendation system algorithms. Using approaches like random search CV, the goal is to ensure that the obtained results run quickly and efficiently on distributed computation disciplines, as these computationally demanding tasks are better handled on distributed systems. Now let's move forward.
Let's now look into collaborative and content-based filtering techniques. Collaborative filtering is a technique used by recommender system to predict what users might like based on the preferences of other users. It's a powerful tool that can be used to personalize recommendations and improve user engagement. It recommends based on nearest simple neighbors with same taste and the past interactions of the users with items. Whereas in content-based filtering is another approach in which a person is recommended with similar items he has interacted with. Now let's look into example. In collaborative filtering, let us say suppose if a person 1 likes a set of movies that are also liked by another person, say person 2. Then person 1 receives a recommendation that is dependent on person 2's liking as well as their own past interactions. In content-based filtering, if person 1 likes a movie, then he gets a movie recommended based solely on the similarity of the movie he liked. Now let's move forward.
Coming to the recommendation systems, the ALS algorithm takes center stage in recommendation systems because nowadays many of large tech companies are using matrix factorization techniques for their recommendations. The algorithms like SVD and SVD++ will run on top of ALS algorithm. Coming to use of SVD and SVD++ in recommendation systems, these algorithms are used to recommend products, movies, which are relies heavily on understanding of user preferences. SVD and SVD++ excel in this task, and by the analyzing user item interactions like rating or purchases, by finding the patterns and similarities between users and items, this predict which item a user might enjoy based on their past behavior and similar user preferences. SVD and SVD++ employ two main filtering techniques, which are collaborative filtering and content-based filtering. As we mentioned before, collaborative filtering focuses on user similarities, assuming users who liked similar items in the past might share interest in future, and content-based filtering analyzes the features of items and recommends the items similar to those a user previously enjoyed. Both are used effectively by SVD and SVD++ to improve recommendation accuracy. Both SVD and SVD++ algorithms rely on matrix manipulation for recommendation generation. The user item interaction matrix acts as the core, storing user ratings or other interaction data, and SVD then decompose this matrix into smaller matrices representing user latent factors and item latent factors. These latent factors capture user preferences and item characteristics allowing the algorithm to predict user item interactions. While both SVD and SVD++ algorithms leverage matrix factorization techniques, they differ in key aspects, where SVD focuses solely on explicit ratings, limiting its effectiveness, which will be affected only on sparse data. SVD++ incorporates implicit ratings, leading to improved accuracy with limited explicit data. Additionally, SVD++ utilizes a backtracking algorithm for optimization, makes it more faster and more efficient than SVD. So SVD++ offers significant advantages over SVD for recommendation systems, particularly when we are dealing with sparse data.
Let's start with the data set. Right? Now this data set is Amazon ratings, which has 4 columns: user ID, item ID, timestamp, and rating. Now this data set has 2.1 billion nodes and 5.8 million edges, and the average degree is around 5. So we can say that this is a sparse network. Now let's go to the code. In the first part, we are setting up the cluster path and starting a Spark session. Next, we load the data set and set up the ALS algorithm. After that, we are defining the parameter grid with the parameters which we are going to optimize. Next, we set the evaluator as regression evaluator and set up the cross validator. Now this part of the code acts as the randomized search CV, and here we store best rank, best iteration, best regulation parameter and print them at the last.
Now coming to the objective of today's presentation, which is hyperparameter tuning, we are going with an approach called random search CV. Random search CV is a technique for hyperparameter optimization that randomly samples a set of hyperparameters that minimizes our objective function, which is the mean square error. The set of hyperparameters we are leaving to optimize is iterations, regularization parameter, and rank. As mentioned here, iteration is the cycle of iterations minimizing the residuals. Regularization parameter is a value that controls the trade-off between fitting the training data and keeping the model simple. Rank, which governs and affects accuracy, efficiency, and interpretability, cold start performance, and recommendation diversity.
Our algorithm is an iterative one, in which in each iteration a set of hyperparameters are sent for the training, and this training takes place on multiple worker nodes. And once all iterations are done, it compares and finds the best set of hyperparameters and prints the result. We use randomized search CV for sending the hyperparameters.
So this is the Amazon's review data set. So I'll just show you the glance of the data set, and here it is. So I'll show you the Java process running behind it. So you can see this data node running. So where we store the data set. And let's start the Spark session for now with only one node just for testing. Yes. So you can see there's one worker alive. So Spark session is running. So this is the code, and we just use only one parameters for once. So if you can see rank, max iter, and regression parameter, and let's start the code now. Yeah, it started running now. So let's go into Spark CUI based, and I can show you more information about it, how process are going on behind it, so on. Here's the application. Uh, yeah, SVDHT is the name of the process going on. So I'll show you the DAG representation of RDD's partitioning, how the mapping works, and so here it the map partitions and so on. Yeah, here it is. So this is the entire DAG representation of how the text being processed into it, how it is accepting, how other nodes are taking it, and all. Yeah. DAG representation of the regression evaluator, how exact this ALS algorithm works, how the text being processed, and how map values, group values combine together, join and map values, and partition it together. So this is the timeline representation of the job being processed. So this is the RDT, how RDT being processed, and then regression evaluator, and how regression evaluator goes into the process, so on. Yeah. So at last we got this MSC as 102.46, which is a pretty good value for now. So let's directly jump into hyperparameter tuning by giving lots of parameters here. So instead of giving only one parameter, we give more than two parameters for validation purposes. And when it fit and gets the best parameters, and then we fit again, we get the best results from this. Hyperparameter tuning in one node, it's not gonna happen. It takes a lot of time, right? So we do it in the large scale. So let's say we connected 7 workers right now. So let's do this in terminal. So before running, let's see the Java process behind it. So there's a master node, worker node, and data node all are running. So let's run the code now. After waiting for a little time, we got these best parameters here, where the rank is 5, number of iterations is 5, regularization parameter is 0.1, where we got the best result with these parameters here in front of you. So the time taken is 4.3. It's pretty good with 7 nodes.
Coming to the results of our execution, we can see as unoptimized, for one number of workers, we got mean squared error of 102. For optimized single worker, we got 3.4 mean squared error. And for optimized 3 worker node, we got mean squared error of 3.6. And for optimized 7 worker node, we got a mean squared error of 3.4, reducing mean squared error and enhancing accuracy. Distributed computing with Spark clusters demonstrated a remarkable reduction in training time, efficiency, handling large-scale datasets. Our project improves recommender systems for temporal data through hyperparameter tuning and distributed computing with Apache Spark. Implementing the SVD++ algorithm showed promising results in optimizing recommendations based on temporal datasets. Hyperparameter tuning significantly improved the algorithm's performance, reducing mean squared error and enhancing accuracy. Distributed computing with Spark clusters demonstrated a remarkable reduction in training time, efficiency, handling large-scale datasets. That's it for the presentation today. Thank you.